All right, so this is the assignment 401.3 force and kinematics problem set. So I'll start with just question 1. We'll go through it. It says a 27 kilogram bookcase is pushed with a force of 250.8 newtons so that it accelerates at a rate of 9.29 meters per second. Is noticeable friction present in this scenario? So if you look at this, when you apply a certain amount of force, in this case 250.8 newtons, to something with a mass of 27 kilograms, you would expect it to have a certain amount of acceleration, and you can calculate that. You can use F net equals ma to actually calculate what you would expect that acceleration to be. Okay, and so you can solve for what acceleration you would actually get with that if there was no friction present. So if there is friction present, that means that my acceleration is smaller than whatever that number is. Okay? Or if I get 9.29, if I actually get this number, that means that there wasn't any friction present because I'm getting the number that I would expect to get based on that force and that mass. So that's what you're supposed to do here, is take this force, 250.8, and set it equal to 27, that's the mass, times A, and then see, do I get 9.29 or do I get something smaller? Because if there's friction, I've asked y'all this several times now, how does that affect acceleration? Y'all tell me every time it's less. Okay, so let's see if we get 9.29. Okay, if I want to solve for A, I need to divide both sides by 27, so I'm going to type in my calculator 250.8 divided by 27, and I get 9.29. Okay, which means there is no friction present in this scenario. Okay, if I had gotten, like, let's say 12, okay, instead, like maybe it's supposed to be 12, and I only have 9.29, that means that there was friction present that made it slower or accelerate less than it should have otherwise. Okay, so that's all you're doing here. Do these numbers all work together? Yes, they do. There is no friction present in that scenario. The second question says, if the same bookcase is then pushed with the same 250.8 newtons across a different surface and experiences an acceleration of 4.4 meters per second squared, what is the coefficient of friction between the bookcase and the new surface? Guys, look, I can already tell there's friction because the acceleration should be, based on the force and the mass, it's supposed to be this, 9.29, and I only have 4.4. So I know that it's accelerating less, and the reason it would be doing that is because there's friction on the surface. Okay, and so if you're trying to figure that out, you would need to first figure out what the net force is, because you already know how much force is applied. It's right here. You're applying with that amount of force. So let's figure out what the net force is so we can figure out what the force of friction is. Again, net force is mass times acceleration. It's the same bookcase, so it has the same mass. F net equals, my mass is still 27. My acceleration now, though, is 4.4. So you're going to multiply 27 times 4.4. And you're going to get a net force of 118.8 newtons. Okay, so this is the net force. You pushed with 250.8 newtons, but only 118.8 of those is actually causing the acceleration, which means a bunch of it was canceled out. Remember the other equation for net force, if you can't logically figure out how to get your answer from here for force of friction, if you can't figure it out logically, go back to this. You should know that your net force is the sum of your forces. In this case, you have an applied force and you have force of friction. Okay, those are the only two. You could even draw the diagram if you want, and you'll have a forward arrow and a backward arrow. We don't care about the up and down. We already know those are going to be balanced. Okay, but you're going to have these two. Again, one of them is in the backward direction. The friction, typically, we're going to call it in the negative direction. So you keep that in mind whenever you're doing this, because your diagram might look something like this, okay, with your applied force and then your force of friction. Something like that. Okay, so my net force is 118.8. It is equal to, the applied force in the question is 250.8 plus force of friction. Okay, if I want to solve for force of friction, I just need to subtract 250.8 from both sides. So I'm going to take my 118.8 and I'm going to subtract 250.8 from it. And yes, you're going to get a negative number because friction is in the negative direction. Negative 132 newtons would be my force of friction. Okay, so now we have forces. We could label on this if we wanted to. Okay, but the question doesn't ask for the force of friction, it asks for the coefficient of friction. We do have an equation that has coefficient of friction in it. It says that the force of friction is equal to mu times Fn, which means that I have force of friction, I have I need to get Fn so I can find mu. Now Fn, I told you we didn't really need to draw these forces in because they would be balanced. Because again, this situation describes a bookcase moving across the floor. It doesn't describe any acceleration in the vertical direction, so I know those are equal and opposite to each other. So although I don't have an equation for normal force, I do have an equation for force of gravity. The force of gravity of an object is equal to mass times gravitational acceleration, m times g. So you would take that 27 that's in the question, you would multiply it by 9.8, and that would give you your force of gravity, 27 times 9.8. It also gives you your normal force. They're both 264.6 newtons. And again, they're the same because we don't have any vertical acceleration. So now we're going to plug into this equation. Force of friction, negative 132 equals mu times my normal force is 264.6. Now I'm going to tell you this. Mu is a ratio. It's scalar. It doesn't have direction. So this negative sign is going to make it look like I have a negative mu. You don't. Okay. Whenever you report your answer to mu, you can't have a negative. So if you have a negative there, just don't type it in. Take it off because you're going to get a negative whenever you put force of friction in here. But if I want to solve for mu, I'm going to divide both sides by 264.6. So that's going to be 132 divided by 264.6. And that's going to be 0.498866. It keeps going. 0.499. Because it says give at least 3 decimals. And there's no unit here. Okay, so that's the first one. Let's take a look at the next one. Okay, the second question says, in a lab, a block weighing 68.6 newtons is attached to a spring scale and both are pulled to the right on a horizontal surface as shown above. Friction between the block and the surface is negligible. What is the acceleration of the block when the scale reads 35 newtons? You've seen this question before. It's just telling you that this force right here is 35 newtons. Because there is negligible friction, this will be the only force causing this block to accelerate, the only horizontal force. So this is also your net force. Okay, it's the only force there. So if you wanted to solve for acceleration, you would again use the same equation, F net equals ma. We have F net, it's 35, but we need mass in order to find acceleration, and right now we have weight. Okay, so in order for us to answer this question, we need to figure out what the mass of this is. I know that the weight, Fg, is equal to mass times gravitational acceleration, and I know the weight is 68.6. Technically, that's negative 68.6 equals mass times my acceleration due to gravity, negative 9.8. So if I want to solve for the mass, I just divide both sides by negative 9.8. Those negatives are going to cancel. So 68.6 divided by 9.8 gives me my mass of 7 kilograms. And now I can solve for the acceleration. Okay, again, F net equals ma. F net is the 35 Newton force because there is no friction on that. It's the only force in the horizontal direction. The mass is 7. We're looking for A, so we're going to divide both sides by 7. Okay, and 35 divided by 7 is going to give us our acceleration, which of course is 5. Okay, so our acceleration is going to be 5 meters per second per second. The second question says, if the block is initially at rest and experiences this acceleration for 1.4 seconds, how fast will it be moving at the end of this time? So this is the new part where we bring in kinematics. Okay, so I have now an acceleration of 5 meters per second squared. Okay, this question tells me that my initial velocity is 0 because it says it starts at rest. It tells me that it accelerates for a time of 1.4 seconds, and it says and it asks for the velocity at the end of that time. How fast is it moving after that? So these are the variables that we have and the one we're solving for. This is when you take a look at your equations, your kinematic equations, and you look for one that has acceleration, initial velocity, time, and final velocity in it. And hopefully you can see pretty quickly it's the first one on my board. VF equals VI plus A times T. Okay, so this is what you're going to substitute into. VF equals 0 plus A is 5, T is 1.4, and that will give us VF. Okay, the 0, of course, we don't have to worry about, so it's just 5 times 1.4, and that'll give us our final velocity. 5 times 1.4 is 7. So my final velocity is 7 meters per second. All right, the next question says, if a 5 kilogram toolbox is ejected from a space shuttle in deep space, how much continual force is required to keep it in motion? Okay, and this goes back to Newton's first law. An object at rest will remain at rest. An object in motion will remain in motion with a constant velocity unless acted on by an outside unbalanced force. You don't need force to keep something moving if you're in space. There's no other forces there to slow it down. It will continue moving all by itself until there's some force acting on it. So how much force is required? None. You don't have to do any math here. It might look like a math question, it's not. Question 4. Question 4 says, Thomas and Kelsey apply at 80.4 newtons of force to the left when moving a 54.7 kilogram sofa, causing it to accelerate across a frictionless floor. What is the acceleration of the sofa? Okay, so they are applying a force to the left of 80.4 newtons. Okay, that's their applied force. It says there's no friction, so that will be the net force as well. There are other forces here, but again, it's going across the floor, and these two forces, Fn and Fg, will be equal and opposite to each other. So my net force is 80.4 newtons. I have the mass there, and I can just go F net equals ma, with my net being 80.4 and the mass being 54.7. I can solve for acceleration. 80.4 divided by 54.7 gives me 1.47 meters per second squared. And again, the direction is to the left. It's in the same direction as the net force. If they use the same amount of force to move another piece of furniture with 2 times the mass, how will its acceleration compare? We just talked about this. If you have 2 times the mass, okay, then you're going to have less acceleration. Okay, in fact, you would have 1/2 as much. They are inversely proportional to one another. But that's Newton's second law. Question number 5 says, a force of 1,840 newtons acts on a 1,890 kilogram car for 52 seconds. Assume the car is initially at rest. How far has the car traveled after 52 seconds? Okay, so they give us the force and the mass. I know right off the bat, they give us a lot of stuff. In fact, a good idea here would be to label everything so you can see what to do with it, because I know what to do with it, but you might not looking at it unless you label it. So your net force, the only force you have to worry about here is this 1840. Okay, we have the mass is 1890. We have a time of 52 seconds. We have an initial velocity of 0 meters per second. And we're looking for how far the car travels at the end of that. Okay, so looking at these show up in my kinematic equations, the ones on my board behind me. Okay, but in order for me to use this, I need the acceleration. That's what I'm using this for. Okay, if they give you a force, a net force and a mass, find acceleration, and then you can use that acceleration down here with your kinematic equations in order to solve for the missing variable. Okay, so your first step is going to be using F net equals m times a. Because you have the stuff to do it, just do it. Okay, if you don't have acceleration already, find it, because it's in both boards. Okay, that's going to be your first step. Okay, so F net is 1840 equals the mass 1890 times A. You're going to divide 1840 by 1890. That's going to give you your acceleration as 0.9735 meters per second squared. Okay, so I have an acceleration now. It was initially at rest, so it's moving it positively. It's making it move. Okay, it doesn't say backwards. We're just going to go with that. Although it only asks for distance, we don't really care about the direction. Now I have A, T, and VI, and I'm looking for delta X. Again, take a look at your kinematic equations now. That's where these variables show up. And the one that you have enough information to use is this one. Delta X equals VIT plus 1/2 AT squared. That will allow me to solve for delta X using the information that I have. Okay, so VI is 0, so VIT is going to be 0 plus 1/2 A, sorry, not A, I have a number for that, 0.9735 times T, I have T as well, don't I, times 52 squared. Okay, and that's going to equal delta X, which is what I'm trying to find. So let's take this number and get half of it. So divided by 2, and then multiply it by 52 squared. And we get 1316.2328, and it keeps going. But all we need to do is type that over here, 1316.23. Okay, so you're using both force equations from this unit and kinematic equations from earlier in the year to solve ones like this. All right, this one says a 1,587 kilogram car begins at rest. Again, I'm just going to label it as we go. I have a mass, 1587 kilograms. I have an initial velocity of 0. It began at rest. I have a displacement of 208 meters. I have a time of 70 seconds, and I'm trying to find net force. Okay, well, in order for me to find net force, I need mass and acceleration, which means I need to find acceleration because I don't have it. But I do have a bunch of these variables that show up in my kinematic equations. Again, the ones behind me on my board. VI, delta XT, I'm looking for A. These are the same combination of variables I had up here. It's the same equation. Delta X equals VIT plus 1/2 AT squared. This time though, we're gonna solve for A. Delta X is 208. VI is 0 times anything is still 0. Plus 1/2. A is what we're looking for times 70 squared. Okay, so 70 squared divided by 2, half of 70 squared, is this number. So let's rewrite this. So 208 equals 2450 times A. Now we're going to divide both sides by 2450. 208 divided by that answer gives me my acceleration of 0.085 if I round it, meters per second squared. Okay, now I can use that to find net force because I know the mass, and I know F net equals ma. So it's equal to the mass, 1587, times that number I just got, 0.085. That'll give me my net force. So I'm going to take my answer and I'm going to multiply it by my mass, 1587, and I'm going to get a net force of 134.6 36.73. And guys, don't round until the end. You'll notice I use the exact answer from the calculator. If you round at this step, it may give you rounding error, and then it's going to count it wrong. All right. Oops, that's the wrong button. Okay, so let's look at number 7. Again, this is 4.1.3, Force and Kinematics problem set. Number 7 says, a kid riding a bike with a total mass of 36.3 kilograms is moving at 13.5 meters per second when he stops pedaling and coasts to a stop due to friction. If the coefficient of friction between the bike tire and the pavement is 0.61, what is the stopping distance for the kid bike system? Okay, so we're ultimately going to be having to figure out stopping distance. And stopping distance or distance of any kind doesn't show up in my force equations, which means I'm going to have to use my kinematic equations to help me finish out this problem. But I can only use my kinematic equations if I know enough of the variables, and one of those is acceleration, and I don't have that one. And so typically on these problems you're going to have to either start with a kinematic equation to get acceleration or to start with a force equation to get acceleration and then use it in the other one. In this situation, it's going to ask us to start with our forces. So first of all, let's talk about what forces are acting on this kid bike system. Okay, obviously we have the force of gravity. That's the weight of these two objects together. It does give me their total mass, so I could solve for that if I want, but I have Fg. Okay, I also have Fn, my normal force of support from the roadway. I know that this bike is not accelerating vertically, it's just coasting to a stop along the roadway, so I know that these forces will be equal and opposite to each other. But I know there's friction because the question says so. It says that he's moving at 13.5 meters per second when he stops pedaling and coasts to a stop due to friction. So I know that friction's going to oppose his motion. Okay, and it talks about him moving in a positive direction, so I'm going to put my friction in a negative one. Okay, is there an applied force here? No, it says he stops pedaling. He's coasting. The only horizontal force acting on him is friction. He's moving to the right, but because friction is acting against him, he's going to slow down until he stops. But that means that friction is my net force. It's the only force that's not canceled out by something else. Okay, and so I know my net force is the force of friction. Okay, now it doesn't tell me what that force of friction is, but it does tell me the coefficient of friction. And I have an equation that I can use to solve for force of friction. Force of friction is equal to mu times Fn. Okay, and so if I can get normal force, I can multiply that by this 0.61, and then I'll have my force of friction. And my normal force, as we already determined, is equal and opposite to Fg. And I do have an equation for Fg. Fg is mass times gravitational acceleration. In this question, the total mass is in that first sentence. It tells me that the total mass is 36.3 kilograms. We're going to multiply that times 9.8 to get the magnitude of the weight, 355.74. That is also the magnitude of the normal force. They are both equal to 355.74. And so if I want to solve for the force of friction, it's mu times Fn. It's equal to, the mu is in the question, 0.61, I have it highlighted, times Fn, 355.74. And that's going to determine my force of friction. So I'm going to take my answer and I'm going to multiply it by 0.61. And that gives me a force of friction of negative 217.0014. I know it doesn't say it's a negative number. It's not going to give me a negative, but I know it's negative because I know it's going opposite my motion. Okay, so my force of friction, which is my net force, F net, is that value right there, negative 217.0014 newtons. And the reason I need to know that this is my net force is because now I can use my net force equation to find acceleration, and then I can use acceleration to find this distance with my kinematic equations. So F net equals ma. I have my net force, negative 217 equals, I'm just rounding it now, but I will use the whole value in a minute. The mass in the question, 36.3 times A. So if I want to solve for A, I'm going to divide my 217, and technically this should be negative, divided by 36.3, and I'm going to get, and again this should be negative as well because I didn't type it in here, but negative 5.978. Okay, again, this is not my answer, this is the acceleration, negative 5.978 meters per second squared. Okay, so let's see what else I have. I have that acceleration. I have an initial velocity, because it says he's initially moving 13.5 meters per second, and then he coasts to a stop. So I have a final velocity of 0. Okay, so I have those things, and it wants to know the stopping distance. So it just gave me these 3. Well, it gave me 2 of them. I calculated the acceleration. So I can solve for delta x, which is going to be his stopping distance. I can find this from the information I do have. If I look at my kinematic equations, one of them has acceleration, VI, VF, and delta x in it. And it is the second one on my board. This equation right here. VF squared equals VI squared plus 2 times A times delta x. Equation with the information that we have here. So VF is 0. 0 squared equals 13.5 squared plus 2 times negative 5.978 times delta x. This will allow us to solve for delta x once we've rearranged this. Keep in mind, you are going to end up with a wrong answer if you do not have your signs correct. So the fact that he is slowing down, you need to make sure that you know that's a negative acceleration. 0 squared, of course, is 0. So let's see what 13.5 squared is. 182.25. Okay, so we're going to move that. So let's subtract this 13.5 squared from both sides. Okay, and that's going to give me, again, negative 182.25 equals, and then we'll multiply this, 2 times negative 5.978, which is equal to negative 11.956 times delta x. So again, from here, if I want to solve for this, I need to divide both sides by 11.956. Sorry, negative 11.956. That's going to cancel. That isolates my variable, and that goes in my calculator. You'll notice the negative signs are going to cancel now. Okay, so we're going to take this and divide it by 11.956, and we get 15.24339. Obviously keeps going, but let's go ahead and type that in. 15.24 meters. Number 8 says a 1,000 kilogram car changes its speed from 8 meters per second to 25 meters per second due to a 1,230 Newton net force. How long does this take? Okay, so again, a good place to start with these is going to be labeling everything, because we don't know exactly where we're starting necessarily just by looking at it. And I have so many equations now to choose from that it's going to be important to label things so we can figure out how to get to the ultimate answer at the end, in this case time. So in this particular question, I have a mass of 1,000 kilograms. I have an initial velocity of 8 meters per second. I have a final velocity of 25 meters per second. I have F net of 1,230 newtons, and I'm trying to solve for time. So from this information, I only know two variables that fall into my kinematics equations, and so that's not actually enough to use any of those formulas. However, I do know mass and net force. That is enough to use this equation. So although we're not trying to solve for acceleration, we're going to start there. And that's almost always where you're going to start, because like I said previously, you're either going to start with the force equations to get acceleration so that you can use it in the kinematic equations, or you're going to start with the kinematic equations to get acceleration so you can solve for something in the force equations. So because acceleration is the variable that kind of ties these two units together, it's typically what you're solving for first. So if we want to plug in, we have 1,230 equals 1,000 times A. So we're going to divide both sides by 1,000 to cancel that. And when you divide 1,230 by 1,000, you're going to get 1.23. So the acceleration is 1.23 meters per second squared. Okay, and again, because it doesn't mention the net force being negative, we're going to assume that this is a positive net force. It actually needs to be because it makes it get faster. So it's in the same direction as this. And so we know our acceleration, we know VI, we know VF. Time only shows up in our kinematic equations, so we're looking at those kinematic equations, and the one that has these variables in it is this one, VF equals VI plus A times T. And so if we substitute in, that is 25 equals 8 plus 1.23 times T. Okay, again, you cannot add these. They are not like terms, so we're going to move the 8 over here by subtraction. Minus 8, minus 8. Okay, so you have 25 minus 8, which is, of course, equal to 17. 1.23 times T. Again, to solve for T, we're going to divide both sides by 1.23. And 17 divided by 1.23 is 13.82. That would be your time, 13.82 seconds. Number 9 says a jet lands on an aircraft carrier with an initial velocity of 77 meters per second. So again, let's label everything. Okay, so my initial velocity is 77 meters per second. It comes to a stop, so there's my final 0 in 2.4 seconds. The average force applied by the braking system. Okay, if it's just trying to stop here and it's talking about the braking system, this is going to be my net force. It's going to be the only force acting in that direction as it comes to a stop. So that net force is going to be negative, because it's trying to slow it down, 47,500 newtons. What is the mass of the jet? Again, mass only shows up in my F-net equation. It's not in any of my kinematic equations. So I can't solve for mass without acceleration and net force. And I don't have acceleration right now, but I do have some information up here that I can plug into a kinematic equation to solve for acceleration. And in fact, it's the same kinematic equation we just used right here. We can solve for acceleration with this. So if I plug in, that is 0 equals 77 plus A times 2.4. Okay, so VF equals VI plus A times T. Again, that's going to move this over here. Negative 77 equals 2.4A. Divide both sides by 2.4. And we have acceleration is equal to 77 divided by 2.4 is going to be negative 32.083 meters per second squared. Okay, this is not our answer, but we need it to find mass. Again, we're going to go now to our F-net equation. F-net equals m times A. We know F-net is negative 47,500. It is equal to m times the acceleration I just found, which is negative 32.083. Again, that is rounded. So in my calculator, I'm going to divide 47,500 by the whole value instead of the rounded one, because I don't want any rounding error in here. And when I do that, I get this, 1,480.52. Number 10. A student pushes a 17.7 kilogram lawnmower. The handle makes a 23-degree angle with the ground as shown by theta. Consider the rightward direction to be positive. If the magnitude of the frictional force is 65.1 newtons, what force must the student apply to the lawnmower to accelerate it at 2.1 meters per second squared to the left? Okay, so there's a lot of information here. We know that there's a force applied at an angle. We know that the magnitude of friction. So let's go ahead and see if we can draw a free body diagram here. So my free body diagram is going to show all the forces acting on this lawnmower. Okay, that force that he's pushing with, we typically draw these forces coming out of the free body diagram rather than going into it. So rather than drawing it here, I'm going to draw it down here instead. Okay, again, that's the same thing. I'm just going to put it like we normally do on our diagrams so that it looks consistent. Okay, so that force right here that is coming down at a diagonal is measured from the horizontal. Okay, and again, this would be the exact same angle here. Y'all should know geometry. Those are the same angle. Okay, but that angle is 23 degrees. Okay, so we have this 23-degree angle right here, which is represented by theta. We know that our lawnmower also has a force of gravity on it, so that's Fg. We know that there is some amount of normal force. That normal force, because he's pushing at this angle that is also downward, okay, I know that my normal force is going to equal the sum of these two together. They're both down, so I would add them. And I know that because my lawnmower is not accelerating vertically. Okay, and so I'm actually going to have a pretty lengthy vector up here for normal force. From here, I know that the force of friction, which is going to oppose the motion, so if he's pushing this way, friction is going to be this way. Okay, and I know that the force of friction is 65.1 newtons. And it wants to know what force he must apply to make it accelerate at 2.1 meters per second to the left. Okay, so it gave me an acceleration and it gave me a mass. I can actually solve for the net force. Now, the net force isn't necessarily the answer that I'm looking for, but I can use it to find the answer that I'm looking for. So I'm going to say F net equals m times a. And mass in this case is 17.7. The acceleration is 2.1 meters per second squared to the left. That's going to be negative 2.1. And so I'm going to multiply 17.7 times negative 2.1. And I'm going to get negative 37.17 as my net force. All right, so we have our net force. That is the sum of the forces acting on the object. Now I have several of these forces drawn, but I don't have all of them yet. I need to use this net force is going to help me figure out some of these over here because those are the ones I am missing. I do actually have enough information to find Fg, so let's go ahead and do that. It's mass times gravitational acceleration, which is going to be that 17.7, that mass that's still highlighted, times negative 9.8. And that's going to give us an Fg of negative 173.46. Again, I know it's negative because it's downward as well. But that's Fg. Okay, now the reason I needed F net is because, remember, my vertical forces are going to be balanced. Okay, I have the y component of this force here. It's going to add with this to give me Fn. But this also has an x component. Now the x component of this force is what's going to be responsible for the acceleration of this object, because I have two forces in the horizontal direction that don't cancel each other out. And I know they don't cancel because it says it accelerates this way. So I know this one's bigger. Okay, I also know my net force is that way, so I know this one's bigger. It needs to be bigger by 37.17 newtons. So the net force is going to help me find the x component. Because again, the net force is responsible for the acceleration. The acceleration's to the right, that means the net force is to the right. So this is not telling me about this one that's at an angle. Instead, it's telling me about the x component of that force. And so if I want to solve for that, again, my net force in the x direction is equal to my forces that are going to the left plus my forces that are going to the right. Okay, so in this case, that's going to be, the left is going to be my x force, Fx if you want to call it that. The force to the right is going to be my friction because of the way this diagram is. Okay, and that's going to be equal to the net force, which is going to be negative 37.17.
I need them back to
okay.
do stuff, but I just wanted you to see what we ended up with.
Okay.
Before I made additional comments.
Is the value we found up here a minute ago, negative 37.17. So you're just plugging it into this equation because the net force is the sum of my forces. If I want to solve for this x component, which is the other piece of the total net force, I need to isolate that variable, which means I need to subtract 65.1 from both sides. Again, it's important for you to keep your signs correct here, otherwise you won't get the right answer. So negative 37.17 minus 65.1 is equal to negative 102.27. That means the force in the x direction is negative, which it should be, 37.17 newtons. Okay, so my x component is going to be negative 102.27. That, let's see. Force the student must apply. Oh, okay, so that's actually not his applied force. So what we just solved for was the x component of his applied force is negative 102.27 newtons. So again, his force is applied at an angle. Okay, this is the applied force. There is a component of it going this way. That component is what we just solved for, and it's 102.27. We also know the angle is 23 degrees. We don't know the other component. We could solve for it, but we don't actually need it to answer this question. We can use trigonometry to solve for the hypotenuse of this right triangle because we know the adjacent side and the angle. And if you're trying to solve for the hypotenuse and you have the adjacent side, you're going to be using cosine. It's the ka in SOHCAHTOA. So we're going to say that the cosine of 23 degrees is equal to the adjacent side, which is the number I just found, 102.27, divided by the hypotenuse. I'm not going to put the signs in here because we're really just solving for the magnitude. The direction will be determined by the diagram. So I dropped the negative whenever I solved this. This is sometimes an issue for students algebraically. You cannot solve for this when it's in the denominator of a fraction. So your next step is to multiply both sides by that applied force to cancel it. And now you have FA times cosine 23 equals 102.27. If you want to isolate that variable now, you're going to divide both sides by cosine 23 degrees. And that gives you an applied force is equal to 102.27 divided by cosine 23 degrees. Okay, again, when you actually solve for this, you do need to be in degree mode. So let's go ahead and type it in. So 102.27 divided by cosine 23 degrees gives me 111.102. That is his applied force. That is this force that was applied at an angle, and that's the answer to the question. So it's several steps to get there, and you don't want to just put the net force, you don't want to put just the horizontal component, you need to get all the way to this point. And mine is 111.10. newtons. If the length of the yard is 18 meters and the lawnmower is initially at rest, how long will it take the mower to accelerate the length of the yard? Okay, so now I have the applied force, but that's actually not what we need in order to find this. We actually just need the net force, and we found the net force way up here. Okay, so we're going to use, and actually we don't even need that. We have the acceleration given to us, but if we didn't have the acceleration given to us, we would need to use the net force to find it. Okay, in this particular question, they actually gave us the stuff that we needed. So our acceleration, let's go ahead and list everything, is negative 2.1 meters per second squared. The length of the yard, they just gave us delta x, is 18 meters. He is pushing it to the left in the diagram, so that means his displacement will also be to the left. So I'm going to call it negative 18 meters. The lawnmower is initially at rest, so the initial velocity is 0 meters per second, and it wants to know how long it will take to accelerate the length of the yard. So you're looking now at your kinematic equations, because that's where you're going to find variables like these, a, delta x, vi, and t, and the one that has these variables in it is this equation, delta x equals vit plus 1/2 a t squared. Delta x is negative 18. Vi is 0, so vit is going to be 0. 1/2 times negative 2.1 times t squared. Okay, so let's get half of negative 2.1. Okay, and that's going to be this. Negative 18 equals negative 1.05 t squared. We're going to divide both sides by negative 1.05. Those negatives are going to cancel. So 18 divided by 1.05 is going to give us this, but this is not our answer. This is t squared, so we still need to take the square root of that value, and that's going to give us our answer, 4.14 seconds. Oh, I just realized I forgot my negative sign. See? Let's see. At least I'm assuming that's what the issue was here, unless I rounded somewhere. Let's see. Yep. All right. Okay. This is the last question. It is number 11, and it is about a teacher moving a desk across the room. So, it says, a teacher moves a 17.5 kilogram desk, so it gives us a mass. Let's go ahead and list everything so we know what to do, or at least have an idea of where to start. 17.5 kilograms. We have an applied force at an angle. So again, whenever we actually go to use these numbers, we don't want any forces at angles. I'm not even going to bother writing this down because I need to get the components of it. I need the vertical and horizontal pieces of this force, not the total. Okay, the coefficient of friction, though, I'll go ahead and copy down. 0.46. Okay, so I'm going to start by getting the components of that force. So we have this force that's applied. It is a 173 Newton force, and it's applied at an angle. That angle is 36 degrees. Okay, so you're going to have to find the components. Some amount of this force is in the x direction. Some amount of this force is in the y direction. You need to find both of those pieces in order to answer the questions that you're going to be asked here. If I want to solve for the x direction, it is adjacent to the angle. I have the hypotenuse. Again, if you look at that acronym, SOHCAHTOA, okay, it helps you remember your equations, but I'm solving for adjacent. I have the hypotenuse. Adjacent and hypotenuse show up in the cosine equation. So we would say that the cosine of 36 degrees is equal to the adjacent side, that's f sub x, over the hypotenuse, 173. Okay, and so you end up multiplying 173 times cosine 36. Okay, to get your x component. So let's go ahead and do that. 173 times cosine 36 degrees, and that gives us f in the x direction is equal to 139.96. That's rounded, but we'll go ahead and write that. Okay, so that is the applied force in the x direction. Okay, we can also do the same thing for the y direction, but it's going to end up being sine because it's opposite. So opposite my angle hypotenuse, opposite hypotenuse is here. It's going to end up being 173 times sine 36. And that's going to give us a y force of, and again this is upward, this one's to the right, so these are both positive, of 101.687 newtons. Okay, so that's basically what we're provided with in the question. We have the mass, we have the coefficient of friction, okay, and then we have this angled force, but we really need the components. I can draw in the rest of the forces if I want to go ahead and draw a free body diagram, and I can show now that I have this upward force Fy of 101.687. I have this rightward force of 139.96. Again, those are the two components of the angled force. I have Fg. Fg is going to be equal to m times g. The mass was given to me, 17.5. So let's go ahead and multiply 17.5 times 9.8. And that gives me my Fg is equal to 171.5 newtons. Okay, again, Fg equals mg. That's how we got that. Mass times 9.8. I know that there is still normal force here being applied from the surface that this is being dragged along. So it's dragged across the room, so the normal force from the floor. Okay, now the normal force from the floor in this case is not equal to Fg because there are three vertical forces. These two together need to add up to equal Fg because vertically the desk isn't accelerating. I do need vertical balanced forces. So I need this plus something to equal this. If I want to figure out what that something is, my Fn, I just need to subtract 171.5 minus the 101.687. And I can solve for my normal force that way. Okay, so when I subtracted that 171.5 minus that 101.6868, it keeps going, I get my normal force, which is equal to 69.81 newtons. Okay, and there is friction because it tells me the coefficient, so I know that there's some amount of friction here. Okay, I don't have a number yet, but I have an equation. Force of friction is equal to mu times Fn, and I just found Fn, 69.81 newtons. Mu was given to me, 0.46. So if I want to solve for my force of friction, I'm going to take my answer and I'm going to multiply it by the value for mu that was given to me in the question. And that is my force of friction. It is in the negative direction, so I'm going to label it as negative 32 whenever I write it as an answer. So let's go ahead and do that. Negative 32.11. Fn we found to be 69.81. Fg we found to be this one, which is negative 171.5. What is the acceleration of the desk? Okay, so the acceleration of the desk is going to be due to the net force acting on the desk. I don't have my net force calculated yet, but I do have all of the forces labeled on my diagram now. I have these that I know are balanced and these that I know are not. And so I can solve for my net force in the x direction because it's just the sum of my forces. 139.96 plus negative, keeping in mind to the left is negative, plus negative 32.11, or really what you're doing then is subtracting. Okay, so my net force is going to be that 139.96 plus negative 32.11, or you can write minus 32.11, and I get my net force that way. F net is equal to 107.8459. It's still rounded, but I wrote out still digits here. Okay, so that is the net force. This one is that much bigger than this one. Okay, I can use the net force to solve for acceleration, because if I want to find acceleration, I have to have net force because it shows up in this equation. F net equals m times a. Okay, and so if I plug in, I have 107.8459 equals, the mass was in the question, 17.5 times a. So if I want to solve for the acceleration, I'm going to divide my answer by 17.5. Divide both sides by 17.5. It allows you to cancel over here, and that goes in your calculator, and it's equal to a. The acceleration that I get when I do that is this, 6.16. How far will it travel if it accelerates from rest at this rate for 1.4 seconds? Again, if you ever have a question that says how far, or how much time, or how fast is it going at the end of it, that's when you're using kinematic equations. So, looking at the information we have an acceleration of 6.16 meters per second squared. We have from rest, so we have an initial velocity of 0 meters per second, and we have a time, 1.4 seconds. We're looking for how far, delta x. Okay, so from this, we need to look for these variables in those kinematic equations. And the one that you're going to want to use is the third one on my board. Delta x equals VIT plus 1/2 AT squared. Substituting in, that is 0 times anything is 0. That goes away. So it's 1/2 times a, which is 6.16, times t squared, which is 1.4. That was in the question. So I'm going to take my answer, my 6.16, which I rounded. I'm going to divide it by 2 because I need half of it. And then I'm going to multiply that times my time squared, times 1.4 squared. And I get my displacement. We will have traveled 6.04, if I round it correctly, meters. All right, so again, that is this assignment. You should be able to work through problems just like these, or you can go back and watch this video for extra practice or help.